as x goes to minus infinity of inverse tangent of x. So what does that mean? What does it mean to take the limit as x goes to infinity? What that means is you're thinking about values of the function that are way out there, right? And so to say that this is equal to something in particular is to say that I can make x sufficiently large to get it as close as I'd like to make it to that limiting value. In other words, eventually values of the function are getting closer and closer and closer to the limiting value. So for inverse tangent, we're talking about pi over 2 and minus pi over 2. That's how that goes. How do I know that? Because the inverse tangent's graph is the graph of the tangent for which it's the local inverse. The graph, so inverse tangent is the inverse to tangent restricted to minus pi over 2 to pi over 2. So the domain of the tangent, which is inverted, is minus pi over 2 to pi over 2, not included. So the range of the inverse is that domain, which is namely minus pi over 2 to pi over 2, which is to say that the limit as you go to really, really large positive or negative values is respectively plus or minus pi over 2. So we use the term limit for all of these things. So what's the unifying theme of all these uses of the word limit? Is that we're talking about some kind of process, right? Some kind of process where we're not actually getting to something, but we want to describe that we're getting closer to something in some sense, right? So the careful definition of all these things is in my notes, and they're all made with some kind of dodgy couple sentence hieroglyphic paragraph involving inequalities you guys aren't comfortable with, right? So I'm sorry about that, but that is how they're defined. Now you're like, well, how do people ever find this stuff? Well, this is not how people found things. Newton and Leibniz didn't do these things, all right? Like calculus existed in this sort of semi-formal, very sketchy state for about 200 years. So for about 200 years, we didn't have a careful definition of limit. And for the most part, it was okay. Except that if you asked questions about what's the basis of everything you're doing, you'd find that you didn't really get good answers. This, of course, bothered mathematicians enough till finally various people tried various approaches, but this definition that we have right here is actually from like the 1900s, excuse me, the 1800s, my bad. 1830 or so was this definition, 1850, really popularized by Weierstrass and others. So this is a pretty modern definition, and it's actually far less sophisticated than like what Newton and Leibniz's ideas were, because they actually had much more bizarre ideas about how the foundations of calculus were formed. Well, more bizarre in one sense, but less bizarre in another, in the sense that they actually thought of derivatives in terms of actually being ratios of numbers, as opposed to being captured by a limiting process. So a limiting process is pretty concrete. We have a specific definition, and we can work it out using properties of inequalities and like basic logic that we teach to, well, it's been taught to millions of university students at this point, all right? Maybe not millions. Tens of thousands of university students, maybe 100,000, I don't know. Hey, we're talking about the world, so maybe there's been a million people who've learned this, I don't know. But I will say this, once you really understand the epsilon delta definition, you have separated yourself from the vast majority of humankind that's ever existed. You've understood something that's been hidden to many people through the ages. But that said, we do not function at this level of rigor in this course everywhere. This is kind of a one-off in here. We're going to do this. We're going to understand it as best as we can, and then we're going to go on. And if you don't get it, it's okay. You can still make an A in this course and not get this. But you'd like to try, at least try, all right? And I gave you an example, at least one. We'll do more. Any questions? All right. Well, don't get used to it, but I think we'll end class today here because this is a good place to stop. So.